Hello, this is Group 13, working on the SAD, or the Situational Awareness Device. My name is Emmanuel Ortiz, here working with Thofeng,
Hi, this is Tofal,
Ross Parsons,
and
Hello, this is Ross Parsons.
and Benjamin Quinn.
Hello, this is Benjamin Quinn.
Our project goals were somewhat simple. Create a device that can ensure the safety of first responders, such as being able to scope a room out before entering, or being able to see a hostage situation from a distance. It was to be a throwable device that can send sensor data safely to the first responders, such as if there are deadly gases in the room, or if there are any criminals waiting. The sensor data will then be sent to a mobile application through localhost connection, such as Wi-Fi in a police officer's car, showing what the device can see and hear on the mobile application as far as the Wi-Fi signal can reach.
We had some functional requirements laid out ahead of time that we'd like to meet. A few of them are the system shall be capable of live stream video streaming to a mobile device. We have that working with the VLC library streaming to a Flutter application. The system shall be capable of live audio streaming to a mobile device. We also have that working as demonstrated in our video later in the presentation. System shall have a gas sensor and be able to transmit the data back to the mobile device. We have that working with an MQ2 gas sensor and a script running to check gas levels, and that data is relayed back to the application, mobile application. The system shall be able to survive the impact of being thrown. Um, that requirement was met. We've thrown it off stairs, down a hallway. We have video of that later in the presentation. The system shall be able to orient itself in an upright position. That functional requirement was not met. However, Emmanuel Ortiz was able to add two cameras, one faces each side. So if the camera, or excuse me, the device were to land on one side, film would be taken of the other. System shall be able to transmit its own location. That requirement was not met due to time constraint. The system shall be able to transmit its data up to 200 feet away. Through our testing, we determined it's about 100 to 150 feet, give or take. We believe under the right circumstances that 250 feet data transmission is acceptable. The system shall be functional in both day and nighttime scenarios. We have a night vision camera. We tested it in the daytime. We also enclosed the device into a box, allowing no light in, and was able to get video feedback. The system shall be as cheap and disposable as possible. All things considered, if this device were used in the military or in the public sector, this device is considered pretty cheap. The system's battery shall last at least 15 minutes. Through testing, that was met pretty clearly. Next. We also laid out some usability requirements. The system shall be accessible to any user with an Android or Apple device. Yes, we were able to use the Flutter application, which is both portable in iOS and Android. The system shall be easy to connect to the user's mobile device as long as the device is given the correct IP address of the Raspberry Pi. That data can be transmitted simply. The user interface shall be user friendly. Yes, that was met. We have 3 buttons in the application, each properly labeled with camera 1, camera 2, and gas sensor with an active stream play and pause button. Also, if the device were to land upside down or in abnormal position, we can also rotate the screen so the user can get a proper orientation of the layout. Next. There are some safety requirements. The system shall not be a fire hazard. Through testing, we haven't came across anything that could pose a fire hazard. The system shall be non-toxic. Yes, it is non-toxic. The system shall have proper insulation on all electronic components. Yes, we use the Raspberry Pi and the sensors, and they are all properly wired and enclosed into a case. The system shall have proper insulation on all electronic components. Yes, that safety requirement was met. The system shall have no sharp edges. Yes, that safety requirement was met. In testing and handling it, pretty vigorously. No sharp edges were found. The system shall be soft enough to avoid inflicting injury in case of accidental contact. Yes, given standard use, this system is accident free. Next.
Hi, this is Tofong. I'm talking about project design. So the situation awareness bot that we have is containing a Raspberry Pi as a microprocessor with a various sensor that embedded into it. And we also have a 3D printed chassis inside a PCV pipe for the housing to hold onto the Raspberry Pi. And we also have a foam cushion for cushion and a stiff wire around the outside thread into both end of the pipe to create a spherical shape to reduce the impact. The housing also feature a few hole drilled into PCB pipe or cut out of the foam to allow the embedded sensor to collect data on the SAT project surrounding. Next slide, please. So this is a circuit diagram that we have for our project. So as you can see, both the microphone and the camera are connected to one of the USB port. Um, each of them will connect to one USB for both webcam and microphone. Each will have their own individual USB, and we also have the um, analog to digital converter connect from the gas sensor to itself and to the Raspberry Pi we showed earlier through our soldering part. We also have a 5-volt battery connect to the Raspberry Pi to power it up, and it's a portable lithium battery that we use. And we also have the on the left hand side was the IR infrared camera that you can use to allow the user to view in the night. Next slide, please. So here is the functional block diagram. So we have all the sensor connect to the microprocessor. So the microprocessor receives the data from sensor, such as camera, microphone, and etc., and send the data through transmitter to be received through a mobile app device. So once the information is received on a mobile device, it will display the data to the mobile device for the user through the Android or iOS application. And this is where you can also use the function on your phone to record your own screen for later usage of the data. Next slide, please. So this is a use case diagram. So as you can see here, we have a diagram of a ball being tossed, and when it landed, we were trying to establish the communication from the mobile device to the ball, and we'll try it at least 5 times. And if it's not working, then we have to say that the equipment is either damaged from the impact or not. But if the communication is able to establish, then we can go to checking the sensor to see if the sensor is still working after being tossed at such a great height or distance, or to check if the wire become loose and one of the sensor cannot be online. But if all sensors are working, then we'll see the sensor functioning to see if the microphone able to receive and transmit clear audio, the gas sensor is able to read a gas signal, and the camera is not cracked. So if everything is worked, then the equipment is working, the ball has survived the impact, and we can uh, clearly state that our situation awareness bot is landed safely. Next slide, please. And here's the our gas sensor design. As you can see, the analog to digital converter is connected to the gas sensor, and then it connects to the Raspberry Pi, as you can see in the diagram, and the breadboard we shown below. And on the bottom right hand side is our analog to digital converter. And on the next slide, we'll show you how it's been soldered together. So next slide, please. So this is actually my soldering design of gas sensor. So we're using a proto board instead of a PCB board because due to time constraint of printing. But as you can see at the bottom, I connect everything together with a solder liquid, and all the solder is completely soldered into places where there's no room for error or wiggles. And the protoboard is hold on to both the converter and the gas sensor to help the limiting the fact of it being too large to fit into our project. So I try to limit as much space as I can and make it as small as possible. Next slide, please. And this is the shell design that I made. So basically, the shell is a 4-inch PVC pipe. Usually, we try and do 3-inch, but the housing unit is not, our 3D print house unit doesn't fit in there perfectly. So we did a PVC, a 4-inch PVC pipe. I drill each three side of the pipe with each side will have 4 wire to help reduce the impact, and the padded foam, the circular padded foam around the pipe is also help to reduce the impact or irresistible damage to the wire that you cannot bring it back to the same spherical form again. And the wire is also helpful because for some people who have small hand that cannot grab into the pipe and throw it correctly, you can always grab into the wire because it's stiff enough for you to throw it without the wire become detached or break loose. Next slide, please.
All right, I'm going to talk about the implementation from the hardware side of this. As Tom mentioned, the core of our project is a 3D printed chassis mounted inside of that PVC pipe. The 3D chassis relies primarily on friction to stay inside of the PVC pipe, although from these wires that have been threaded through the sides of the pipes, they provide a little knot on the inside to stop anything from sliding out. There are 4 foam rings on the outside as well. Those are to help cushion the impact and also slide out to the ends of the PVC pipe to stop the wires from collapsing inwards too much, as when the SAD lands, the wires absorb most of the impact. They can get deformed, so in between throws, you often have to pull the wires out a little bit and reset them to that shape. Next slide, please. This is the 3D printed chassis we're using. It is open on the right side there in the picture. What you do is we have a Raspberry Pi inside of a plastic case. The Raspberry Pi inside of the case gets slid into that right side, again, relying mostly on friction to keep it in place as it was designed to be a fairly tight fit. And then a variety of wires will come out from that Raspberry Pi in this case and get mounted in various pieces of embedded foam and look through some apertures drilled into the outside of the pipe. Next slide, please. This is a picture of the Raspberry Pi in its case, and we have the infrared camera attached via ribbon cable, and our gas sensor / analog to digital converter bit on the protoboard attached on that piece with the 4 wires on the outside. Next slide, please. This is, again, our gas sensor and analog digital converter on a piece of protoboard. It was easier to mount them on the same piece of board to save on space, as the room inside of this pipe is rather limited. Next slide, please. This is what it all looks like together. You've got a bit of a spaghetti tangle on the inside. Basically, you have the Raspberry Pi inside of the case that's got a bunch of wires attached to it. And the case is then slid into that 3D chassis, 3D printed chassis, excuse me. Now that whole arrangement is then slid into the pipe. On the inside of the pipe, you can see the parts of the outside wires in red that were threaded through. Those act as an emergency resort stopper if the impact was too hard for friction to not be effective in slowing the slide. Inside of this, the sensors that are meant to point towards the outside have specially cut out holes in them in those circular bits of foam that act as stoppers on the end, that they're embedded inside of several layers of those. And on the very top, there's a hole that's been drilled into it for that MQ2 gas sensor. So the MQ2 gas sensor is mounted on the top of the 3D chassis. It kind of pokes out the top, and then there's a bit of foam padding underneath it to keep it securely in place. The battery we have slides into a slot made underneath the 3D printed chassis and then is again plugged in there with a little foam stopper. Next slide, please.
Hey, I'm Manuel Ortiz. I'm going to talk about the software implementation. There were some useful libraries that helped us with the project, such as IceCast, ArcIce, and Motion. IceCast was an extremely useful library that allowed us to plant the data received in a localhost server from the DarkIce library that reads our audio data from the microphone. The Motion library gives us a video camera stream on a localhost server as well. All these localhost servers are then streamed to the mobile application for the end user. The setup for these localhost servers weren't too difficult. Since there were modifications to the library that needed to be done, such as motion needed to change in resolution, change in file type, and changes to multiple server and streaming options to make sure the video isn't very delayed and that it fits correctly in a VLC player on a mobile application. Then to connect it to the localhost server, the only thing that was needed was to create a function that can stop and play the server's readings whenever it's needed.
A little bit more on the software implementation. Flutter was used as the front end for the mobile application. Our team decided to go with Flutter. There was a few options available at the start. One was Cordova as a good way to make an application that runs both on iOS and Android. Or Ionic was another front end software for mobile application for both iOS and Android. But we decided to go with Flutter as it is a much newer language, much more flexible and quicker. It was written in Dart, Google's homebrewed programming language. We use VS Code primarily as our IDE, just as a note. The gas sensor, the script to run that was written in Python, and we use a Node.js server to run the Python script through. So just as a little illustration, we have the Raspberry Pi, the gas sensor was hooked up to the Raspberry Pi, and a script was running onto the Raspberry Pi. At the same time, there was a local host with a Node.js server on it, and we could call the Python script through the Node.js, and the Flutter application connected to that Node.js server. And that was how the gas sensor information, like the gas levels, was displayed back into the mobile application. Next.
The project was mostly tested in survivability, so that's a big factor in creating a durable device. If the device is unable to survive a large toss, then the device would be considered obsolete for its uses. We tested it by throwing it horizontally and vertically, such as down a flight of stairs or through a hallway. There was also testing on battery life and distance from the Wi-Fi origin point. Sensors were also tested extensively, since they needed to work in use case scenarios. Tests such as being thrown in the dark room to see if we could see in the dark correctly, or the gas sensor being tested with gases to see if it transmits information correctly. Some challenges we ran into were that the microphone would not fully mount sometimes and a manual reboot would be needed. The sensors were a bit hard to input into the housing, and testing for impact resistance was trial and error, working our way up to larger microcontrollers, but still having the worry of breaking a Raspberry Pi.
As we mentioned earlier in the slides, we have completed nearly all the original objectives. Transmitting the device's own location turned out to be unnecessary in most use cases, as the person using the device would usually be throwing it. So finding it again, generally quite easy. I could see this being a problem if you were buried in some rubble or something after throwing the device, but otherwise not necessary. We had to refactor our housing design to take the budget and time constraints into account. We originally were thinking of making an egg-shaped self-righting mechanism with a weight in the bottom, but that would have required more 3D printing and time than we really had access to, so we ended up making a PPC version instead. Long delays in 3D printing and PCB printing resulted in only having time for a single 3D print, so we never got to get our updated 3D chassis, and we had no time at all to make a printed circuit board. Aside from that, everything else we wanted to do, we managed to do.